4.5 billion years ago, suspended in the freezing, absolute darkness of the Orion Cygnus arm of the Milky Way galaxy, a colossal molecular cloud drifted in unbroken silence. This sprawling structure, known as the solar nebula, spanned trillions of miles across the interstellar void. It was a chaotic, freezing expanse of dust and gas, acting as a quiet graveyard for ancient, long-dead stars and a nursery for new ones. To understand the lifespan of the Sun, one must first understand the raw materials from which it was constructed. The vast majority of this nebula was composed of two fundamental chemical elements: hydrogen and helium. Hydrogen is the lightest, simplest, and most abundant chemical element in the universe, consisting of a single proton orbiting a single electron. Forged in the immediate aftermath of the Big Bang, hydrogen acts as the foundational, combustible building block of the cosmos. Helium, the second lightest element, typically contains 2 protons and 2 neutrons in its nucleus. While on Earth, helium is a chemically inert, harmless gas. In the context of stellar astrophysics, it is the dense atomic ash left behind when hydrogen is burned in the heart of a star. For countless eons, this colossal cloud of hydrogen and helium remained in a state of fragile gravitational equilibrium. However, this balance was eventually shattered. A violent disturbance, likely the cataclysmic shockwave from a nearby exploding star or supernova, slammed into the molecular cloud. This invisible wave of kinetic energy compressed the gas, forcing localized regions to clump together. Once this clumping began, the most relentless force in the universe took over: gravity. The mechanics of how this diffuse cloud transformed into our solar system is explained by the nebular hypothesis. This foundational scientific theory dictates that when a massive cloud of interstellar gas begins to collapse under its own weight, the conservation of angular momentum forces the cloud to spin faster and faster as it shrinks, much like an ice skater pulling their arms inward to accelerate their spin. Over millions of years, this spinning motion flattens the spherical cloud into a massive, rotating protoplanetary disk. The historical importance of this theory cannot be overstated, and its development relied on the minds of 2 distinct visionaries. The first was Immanuel Kant, a philosopher whose vital contribution to the field of astrophysics was the radical proposition that Newtonian physics alone could explain the formation of complex planetary systems from a simple, diffuse nebula, bridging the gap between philosophy and physical mechanics. His conceptual framework was later mathematically proven by Pierre-Simon Laplace. Laplace's crucial importance to the field of celestial mechanics lay in his ability to translate Kant's ideas into rigorous mathematical models, proving that the intricate orbital dynamics of the solar system could be derived entirely from the physical laws of gravity and fluid dynamics, without any need for divine intervention to keep the planets in their orbits. As Laplace's models predicted, as the nebula collapsed, an overwhelming majority of the mass, over 99.8% of the entire cloud, plummeted toward the absolute center of the spinning disk. As trillions of billions of pounds of hydrogen gas collapsed inward, the pressure at the core skyrocketed to incomprehensible levels. This crushing pressure generated immense friction, causing the temperature at the center to rise drastically. When the core temperature reached a staggering 27 million degrees Fahrenheit, a physical threshold was breached. At this extreme temperature, the electrostatic repulsion between hydrogen protons, the natural magnetic force that causes positively charged particles to violently push away from one another, was finally overcome by the sheer, crushing pressure of gravity. This specific moment triggered nuclear fusion. In the realm of astrophysics, nuclear fusion is the thermonuclear process where extreme heat and density force lighter atomic nuclei to violently collide and fuse together into a heavier nucleus. When 4 hydrogen protons are smashed together to form a single helium nucleus, the resulting helium atom weighs slightly less than the 4 original protons. That missing, infinitesimally small fraction of mass does not disappear. It is converted into an apocalyptic amount of pure, radiant energy. When nuclear fusion ignited at the core of the collapsing cloud, a blinding flash of electromagnetic radiation erupted. The outward pressure of this explosive thermonuclear energy pushed back against the crushing inward weight of gravity, achieving a perfect, delicate balance known as hydrostatic equilibrium. The violent winds from this ignition blasted the remaining dust and gas millions of miles out into the void, clearing the inner solar system. The Sun had officially turned on. It had become a main sequence star, beginning a terrifyingly powerful engine of consumption that would dictate the lifespan of the entire solar system. Trapped deep within the overwhelming gravitational well of the Sun, the surviving iron-heavy core of Mercury was locked into the most violently eccentric and elliptical orbit of any major planet in the solar system. Its chaotic, heavily elongated trajectory brings it to a scorching perihelion, its closest approach to the solar furnace, of merely 28,580,000 miles. Yet, at its aphelion, its farthest point, it retreats to a distance of 43,400,000 miles. Because of this egg-shaped path through the void, Mercury accelerates to staggering velocities, traveling through space at speeds peaking at over 105,000 miles per hour. This blistering speed and close proximity to the immense mass of the Sun created an astronomical mystery that baffled scientists for over half a century. In 1859, the brilliant French mathematician and astronomer Urbain Le Verrier meticulously calculated Mercury's orbit. Le Verrier's absolute, supreme importance to the field of celestial mechanics was already cemented in 1846 when he successfully predicted the exact location of the planet Neptune using only pen, paper, and the classical Newtonian laws of gravity, observing gravitational anomalies in the orbit of Uranus. When Le Verrier applied these exact same flawless, proven mathematical principles to Mercury, he discovered a terrifying discrepancy. Mercury's perihelion was slowly shifting, or precessing, around the Sun at a rate that Newtonian physics could not entirely account for. There was an unexplained shift of 43 arcseconds per century. Convinced that the laws of gravity were absolute, Le Verrier hypothesized the existence of a hidden, undiscovered planet orbiting between Mercury and the Sun, which he named Vulcan. For decades, the global astronomical community obsessively hunted for Vulcan, scanning the blinding glare of the Sun, but the phantom planet was never found. The absolute, world-shattering resolution to this mystery did not come from discovering a new world, but from fundamentally rewriting the physical laws of the universe. In 1915, the visionary theoretical physicist Albert Einstein published the General Theory of Relativity. Einstein's supreme importance to modern physics lay in his radical, paradigm-shifting realization that gravity is not a traditional, invisible pulling force stretching across empty space between massive objects, as Isaac Newton had proposed. Instead, Einstein mathematically proved that gravity is the physical warping, curving, and bending of the four-dimensional fabric of spacetime itself. In this staggering mathematical framework, the immense mass of the Sun creates a massive, physical depression in the fabric of spacetime. Because Mercury orbits so deeply within this steep gravitational well, it does not travel in a simple Newtonian ellipse. It follows the curved geometry of warped space. When Einstein applied his new equations to Mercury's orbit, the mathematical result perfectly, flawlessly matched the missing 43 arcseconds of precession. Vulcan did not exist. Mercury's bizarre orbit was the first definitive physical proof that space and time were a flexible, interwoven fabric, forever altering humanity's comprehension of the cosmos. Because of its terrifying proximity to the Sun and the extreme warping of space, for generations astronomers held another fundamentally flawed assumption about the planet. Up until the mid-20th century, the undisputed scientific consensus dictated that Mercury was perfectly tidally locked in a synchronous one-to-one resonance, meaning it perpetually showed only one blisteringly hot face to the Sun, while the other half was condemned to eternal, freezing darkness. This deeply entrenched astronomical dogma was completely shattered in 1965 by the brilliant Italian mathematician and engineer Giuseppe BepiColombo, utilizing radar data gathered from the massive Arecibo Observatory in Puerto Rico. Colombo's paramount importance to planetary science and orbital dynamics was his revolutionary, mathematically flawless calculation that Mercury was not tidally locked, but was actually trapped in a highly complex, bizarre 3-to-2 spin-orbit resonance. He definitively proved that Mercury rotates on its axis exactly 3 times for every 2 complete orbits it makes around the Sun. This groundbreaking discovery completely rewrote the textbooks on how massive gravitational bodies dictate the rotational mechanics of their closest orbiting satellites. Because of this 3-to-2 spin-orbit resonance, the passage of time on Mercury is profoundly alien. A single Mercurian year, the time it takes to complete one orbit around the Sun, lasts exactly 88 Earth days. However, because of its sluggish rotation, a single solar day on Mercury, the time it takes for the Sun to appear to return to the exact same spot in the sky, lasts an agonizing 176 Earth days. This means a single day on Mercury is physically twice as long as its entire year. This bizarre rotational sluggishness, combined with the absolute absence of a heat-trapping atmosphere, subjects the surface of Mercury to the most violently extreme, unforgiving thermal fluctuations in the entire solar system. To understand this, one must look to the physical principles of thermal conductivity and specific heat capacity. In thermodynamics, specific heat capacity is the amount of heat energy required to raise the temperature of a given substance. The silicate rocks that make up Mercury's thin, scarred crust have a very low thermal conductivity, meaning they absorb immense amounts of thermal radiation but do not efficiently transfer that heat deep underground or across the planet's surface. During the agonizingly long daylight hours at the equator, the naked, unprotected rock is continuously bombarded by intense, unfiltered solar radiation, causing surface temperatures to skyrocket to a blistering, apocalyptic 800 degrees Fahrenheit, hot enough to instantly melt lead. Conversely, when the surface finally rotates into the agonizingly long night, the absolute lack of atmospheric insulation allows that immense heat to instantaneously radiate away into the freezing vacuum of deep space. Without an atmosphere to trap the thermal energy, the temperature catastrophically plummets to a freezing negative 290 degrees Fahrenheit. This brutal endless cycle of roasting and freezing physically expands and violently contracts the rocky crust, creating an environment so hostile that it fundamentally challenges the engineering limits of any robotic probe sent to explore its dark, iron-rich mysteries. The irreconcilable conflict between the physicists, who calculated a dying, short-lived sun, and the biologists, who required deep time for evolution, reached a breaking point at the very end of the 19th century. The classical laws of thermodynamics had locked the age of the solar system into a maximum of 30 million years, assuming the Sun was merely a collapsing sphere of gas generating friction. This mathematical prison was only shattered when humanity stumbled into an entirely invisible, terrifying realm of physics hidden deep within the atom itself, a discovery that took place in the heart of France. The epicenter of this scientific revolution was Paris. Geographically situated in the north-central part of the country, Paris was built along a major bend in the Seine River, a critical waterway that cuts through the fertile, sprawling Paris basin. Historically, this location was of paramount strategic importance, originating as a fortified settlement on the Isle de la Cite by the Celtic Parisii tribe, and later conquered by the Romans who named it Lutetia. The city controlled the primary trade and military logistics routes connecting the Mediterranean interior to the English Channel. By dominating this river crossing, Paris grew into a centralized, heavily fortified political and intellectual fortress, projecting French imperial and cultural power across the European continent. It was within the damp, poorly ventilated laboratories of this sprawling metropolis that Marie Curie dismantled the classical understanding of matter. Marie Curie's supreme importance to the fields of physics and radiochemistry lies in her revolutionary hypothesis that radiation was not dependent on the organization of molecules, but was an atomic property belonging to the element itself. By proving that atoms were not solid, indivisible blocks of matter, but complex structures capable of emitting physical pieces of themselves, she became the first woman to win a Nobel Prize and the only person to win in two different scientific fields, fundamentally birthing the modern era of subatomic physics. Curie's groundbreaking work centered entirely on the chemical element uranium. In chemistry, uranium is a heavy, silvery white metallic element belonging to the actinide series of the periodic table, bearing the atomic number 92. It is the heaviest naturally occurring element in the universe, possessing 92 protons and a massive, inherently unstable nucleus. Because of this structural instability, uranium undergoes a continuous, irreversible process of decay. This process is governed by the scientific theory of radioactivity. Radioactivity is the physical phenomenon where an unstable atomic nucleus spontaneously loses energy by emitting ionizing radiation. This decay occurs because the nucleus is violently struggling to reach a more stable atomic configuration, throwing off alpha particles, beta particles, and highly penetrating gamma rays in the process. Crucially, this radioactive decay does not just emit invisible radiation. It releases a continuous, staggering amount of thermal heat. The realization that atoms contained vast, hidden reservoirs of internal energy was formalized across the English Channel by Ernest Rutherford. Rutherford's vital importance to the field of atomic physics was his discovery of the atomic nucleus, fundamentally proving that the vast majority of an atom's mass is concentrated in a microscopic, dense core, and his formulation of the concept of radioactive half-life. He conducted this paradigm-shifting research at the University of Cambridge. Geographically located in the flat, marshy fenlands of eastern England along the River Cam, Cambridge was originally a strategic, easily defensible crossing point surrounded by treacherous bogs, which naturally insulated the academic scholars who fled there in the 13th century, allowing the town to develop into one of the most secluded, prestigious, and formidable intellectual strongholds on the planet. Rutherford realized that if radioactive elements within the Earth were constantly emitting heat, the planet was not simply cooling down from a molten state, it was actively heating itself from the inside. This completely invalidated Lord Kelvin's mathematical calculations regarding the age of the Earth. If the Earth harbored a massive, hidden source of atomic energy, the Sun almost certainly possessed one as well. The discovery of this staggering subatomic energy triggered a shockwave through the scientific community that completely rendered all previous classical theories of the Sun's lifespan obsolete overnight. The abrupt, devastating obsolescence of the old astrophysical models was perfectly mirrored by the sudden, absolute obsolescence in global naval warfare caused by the launch of the British battleship HMS Dreadnought in 1906. Conceived to dominate the oceans, The HMS Dreadnought was a mechanical leviathan measuring 526 feet in length and displacing a colossal 36 million pounds of steel, armor, and weaponry when fully loaded for combat. Unlike any warship before it, the Dreadnought abandoned the traditional mixed-caliber armament in favor of an all-big-gun design. Its primary battery consisted of 10 massive 12-inch, 45-caliber Mark X breech-loading naval guns housed in 5 heavily armored twin turrets. These terrifying weapons could hurl an 850-pound armor-piercing high-explosive Just as the Dreadnought proved that previous warships were fundamentally inadequate for the modern era, the discovery of radioactivity proved that simple gravitational contraction was fundamentally inadequate to power the Sun. The energy locked inside the nucleus of an atom was millions of times more powerful than chemical combustion or gravitational friction. The Sun was not a shrinking ball of gas slowly cooling into the dark. It was an unfathomably powerful nuclear furnace, and its true lifespan was not measured in millions of years, but in billions. However, the exact mechanism of how the Sun accessed this nuclear energy remained a total mystery, requiring a descent into the bizarre, counterintuitive mechanics of the quantum realm. By the 1920s, the astronomical community knew with absolute certainty that the Sun harbored immense atomic energy, but the precise mechanical process of how it extracted that energy remained locked behind an invisible, subatomic wall. The man who first proposed the correct atomic engine was Sir Arthur Stanley Eddington. Eddington's absolute importance to the field of astrophysics was his pioneering theoretical modeling of the internal constitution of stars, single-handedly formulating the Eddington limit. This foundational astrophysical concept mathematically defined the delicate, terrifying balance between the inward crushing weight of a star's gravity and the outward explosive pressure of its internal radiation, essentially dictating the maximum possible luminosity a star can achieve before it violently blows its outer layers into space. Eddington formulated and delivered his groundbreaking papers in London. Geographically situated in the southeast of England, London is anchored by the River Thames, a massive, meandering navigable waterway that cuts through the London Basin and empties directly into the North Sea. Historically established as Londinium by the Roman Empire in the 1st century, the city's paramount strategic importance lay in its deep-water port capabilities, which were naturally protected from sudden naval assault by the winding, easily defensible estuary. This geographical fortress allowed London to evolve into the undisputed financial, political, and logistical heart of the British Empire, projecting global maritime dominance by maintaining absolute control over the flow of international trade and global naval deployment across the oceans. It was within the intellectual societies of London that Eddington boldly proclaimed that the Sun was generating its heat by fusing hydrogen into helium. However, classical physics immediately raised an insurmountable, mathematically impenetrable wall known as the Coulomb barrier. The Coulomb barrier is the physical law of electromagnetism dictating that particles possessing the same electrical charge, like two positively charged hydrogen protons, will violently and exponentially repel each other as they get closer. To fuse together into a heavier element, these protons must physically smash into one another. At the absolute core of the Sun, the temperature is a staggering 27 million degrees Fahrenheit. While this represents an apocalyptic level of thermal heat, classical thermodynamic equations proved beyond a shadow of a doubt that the protons were simply not moving fast enough to overcome their mutual electromagnetic repulsion. According to the strict laws of classical physics, nuclear fusion in the Sun was completely, absolutely impossible, as the protons would always bounce off the Coulomb barrier before they could touch. This concept of facing an impenetrable, heavily fortified defensive barrier, and the absolute necessity to bypass it rather than simply smashing against it with brute force, was perfectly mirrored in the brutal skies over Europe during the Second World War by the British de Havilland Mosquito FB Mark VI. This was a specialized twin-engine, two-seat multi-role combat aircraft, famously and radically constructed almost entirely out of compressed wood, utilizing balsa and birch plywood bonded with casein glue to save the Empire's strategic metal reserves. Measuring 41 feet in length with a wingspan of 54 feet and 2 inches, this wooden Leviathan was powered by two monstrous Rolls-Royce Merlin 25 liquid-cooled, 12-cylinder V-engines. Each of these mechanical beasts generated 1,620 horsepower, turning three-bladed constant-speed propellers to push the aircraft to an astonishing maximum speed of 378 miles per hour at an operating altitude of 13,200 feet. The Mosquito was armed with a devastating, concentrated forward-firing battery of four 20mm Hispano Mark II cannons and four 0.303-inch Browning machine guns housed entirely in its solid nose, alongside an internal bomb bay capable of carrying a 2,000-pound payload of high-explosive ordnance. Because it completely lacked heavy defensive steel armor, the Mosquito did not attempt to absorb or deflect enemy anti-aircraft fire. Instead, it relied entirely on its overwhelming speed and its wooden, naturally radar-absorbent airframe to effectively slip undetected through heavily fortified German anti-aircraft barriers and Luftwaffe interceptor screens. It bypassed the impenetrable defenses entirely, delivering catastrophic kinetic and chemical energy directly to high-value targets before the enemy could effectively engage. Just as the Mosquito bypassed the physical defensive barrier of the German war machine, in the bizarre, highly counterintuitive realm of quantum mechanics, a subatomic particle like a proton does not have a definitive, absolute location in space. Instead, it is mathematically defined by a wave of probability, meaning there is a smeared chance it could exist in multiple places at once. When two protons rapidly approach each other in the superheated core of the Sun, their probability waves overlap the supposedly impenetrable Coulomb barrier. Because of this wave-like nature, there is an infinitesimally small, but mathematically non-zero, probability that a proton will instantly tunnel through the barrier and spontaneously appear on the exact opposite side, completely bypassing the electromagnetic repulsion without ever possessing the kinetic energy required to physically break through it. Once the proton successfully quantum tunnels through this invisible wall and gets unimaginably close to the other proton, an entirely different fundamental force of the universe takes over: the strong nuclear force. The strong nuclear force is the most powerful of the four fundamental interactions in nature, approximately 100 times stronger than electromagnetism. However, it only operates at incredibly microscopic, subatomic distances, specifically on the scale of a femtometer or 1/4,000,000th of a meter. Its sole, vital physical purpose is to bind protons and neutrons together to form an atomic nucleus, completely overpowering the violent electromagnetic repulsion that would otherwise instantly tear the atom apart. This bizarre phenomenon of quantum tunneling is the absolute master key to determining the lifespan of the Sun. Because tunneling is a probabilistic event, it is exceedingly rare. If protons could easily and classically overcome the Coulomb barrier, the entire massive supply of the Sun's hydrogen would fuse almost instantaneously. The star would detonate in a catastrophic, galaxy-illuminating thermonuclear explosion in a matter of seconds, leaving nothing but a dead remnant. Instead, because an individual proton inside the solar core must wait, on average, billions of years to successfully tunnel through the barrier, the solar engine is heavily and naturally throttled. This quantum bottleneck forces the massive star to consume its hydrogen fuel supply agonizingly slowly. It is this exact subatomic rarity that grants the Sun a stable, steady lifespan of roughly 10 billion years, ultimately providing the Earth with the deep, uninterrupted geological time absolutely necessary for the evolution of complex life. With the realization that the Sun was powered by quantum tunneling bypassing the impenetrable electromagnetic barriers of hydrogen protons, as shown previously, humanity finally grasped the invisible mechanics of the solar engine. However, the precise, step-by-step chemical and nuclear pathway of how hydrogen was physically stitched together to create heavier elements and release apocalyptic amounts of energy was fully illuminated by the brilliant theoretical physicist Hans Bethe. Bethe's absolute importance to the field of nuclear astrophysics was his definitive, mathematically flawless formulation of stellar nucleosynthesis, specifically identifying the proton-proton chain reaction as the exact mechanism that powers main sequence stars like our Sun, an achievement that rightfully earned him the Nobel Prize in Physics. He conducted this paradigm-shifting theoretical research at Cornell University, located in Ithaca, New York. Geographically situated at the extreme southern tip of Cayuga Lake within the sprawling Finger Lakes region of central New York State, Ithaca is topographically characterized by incredibly deep, plunging gorges, towering waterfalls, and sheer cliff faces carved out by massive retreating Pleistocene glaciers. Historically, this rugged, heavily striated, glacially scarred terrain provided a naturally insulated, highly defensible academic fortress, completely isolated from the easily accessible, vulnerable coastal cities. This supreme strategic and geographical isolation allowed Ithaca to evolve into an untouchable, fiercely independent intellectual powerhouse during the tumultuous 20th century, enabling scientists to focus heavily on advanced theoretical physics and engineering without the immediate, paralyzing threat of naval bombardment or coastal disruption. Within this intellectual fortress, Bethe mapped out the proton-proton chain. In astrophysics, the proton-proton chain is a complex, multi-step thermonuclear reaction. Inside the 27 million degree Fahrenheit core of the Sun, when two hydrogen protons successfully utilize quantum tunneling to fuse together, they instantly emit a positron and a neutrino, violently transforming one of the protons into a neutron. This creates a nucleus of deuterium. In chemistry and nuclear physics, deuterium is a highly stable, heavy isotope of hydrogen containing one proton and one neutron, effectively holding double the mass of a standard hydrogen atom. When this newly forged deuterium nucleus violently captures another high-speed proton, it creates a light isotope of helium, known as helium-3. Finally, when two helium-3 isotopes collide with catastrophic kinetic force, they fuse to forge a highly stable helium-4 nucleus, ejecting two excess protons back into the core to repeat the cycle. During this violent subatomic forging process, a staggering amount of mass is lost and converted entirely into raw energy, instantaneously liberated in the form of a photon. A photon is an elementary quantum particle, a completely massless unit of light and electromagnetic radiation that acts as the fundamental, unbreakable carrier of the electromagnetic force throughout the entire universe. Once this newborn photon is forged in the crushing pressure of the solar core, it begins a desperate, agonizing journey to escape the Sun. It immediately enters the radiative zone. The radiative zone is a vast, terrifyingly thick layer of the Sun where the plasma is so unimaginably dense that a single cubic inch of it weighs nearly half a pound. In this crushing, claustrophobic environment, the photon is physically incapable of traveling in a straight line. It travels a mere microscopic fraction of an inch before violently crashing into a densely packed, superheated electron or proton. Upon impact, the photon is instantly absorbed and then immediately re-emitted in a completely random direction. This grueling physical phenomenon in stellar kinematics is known as the random walk. Because of this chaotic, zigzagging, highly contested trajectory through the impenetrable density of the solar plasma, a single photon forged in the core takes anywhere from 100,000 to 170,000 years to brutally grind its way out of the radiative zone. This grueling, highly contested, armor-bashing journey through incredibly dense, hostile territory was perfectly mirrored in the grinding terrestrial combat of the European theater during the Second World War by the deployment of the American M26 Pershing heavy tank. Conceived specifically to violently break the bloody stalemates of heavily fortified, deeply entrenched defensive lines, the M26 Pershing was a mechanical behemoth measuring 28 feet and 4 inches in length and displacing a colossal 93,000 pounds of steel, ammunition, and machinery when fully loaded for combat. Unlike the lighter, more agile medium tanks of its era, this heavily armored fortress was strictly designed to absorb catastrophic kinetic punishment, boasting 4 inches of sloped, cast steel frontal armor intended to safely deflect high-velocity anti-tank munitions. To propel this massive weight through dense urban rubble, shattered forests, and deep mud, the beast was powered by a monstrous Ford GAF liquid-cooled V8 gasoline engine, generating 500 net horsepower. This mechanical giant utilized a revolutionary, highly complex torsion bar suspension system to evenly distribute its crushing weight across 24-inch wide steel tracks, allowing it to relentlessly push forward against immense physical and geographical resistance. Its primary offensive capability was concentrated in an imposing 90mm M3 rifled tank gun, housed in a heavily armored cast steel turret. This devastating weapon could hurl a 24-pound armor-piercing, high-explosive projectile over incredible distances with enough kinetic energy to completely shatter the thickest concrete enemy fortifications. Just as the M26 Pershing had to continuously absorb massive impacts and forcefully grind its way through impenetrable, deeply layered enemy defensive barriers at an agonizingly slow, brutally contested pace, the newborn solar photon must continuously smash into and push through the densely packed, hostile plasma of the radiative zone for hundreds of millennia. Finally, after enduring hundreds of thousands of years of microscopic collisions, the surviving photon reaches the outer boundary known as the convective zone. Here, the internal temperature of the Sun drops significantly to roughly 4 million degrees Fahrenheit, and the plasma becomes slightly less dense. Because the cooler plasma is largely opaque to the radiation, the energy is no longer transferred by light bouncing off atoms. Instead, the plasma itself behaves exactly like boiling water in a massive pot. Giant columns of superheated gas physically trap the heat and aggressively rise toward the surface through the physical process of thermal convection. This violent, boiling ascent is incredibly fast, carrying the photon upward in only a few weeks. The photon finally breaches the photosphere, the blindingly bright, visible surface of the Sun, and is violently launched into the freezing vacuum of space, traveling the 93 million miles to Earth unimpeded in just 8 minutes and 20 seconds. This continuous, highly stable process of thermonuclear fusion, followed by the agonizingly slow internal transport of light, defines the primary lifespan of the Sun, ensuring the steady, unchanging warmth that allowed the Earth's oceans to remain liquid and biology to thrive. However, this magnificent era of stability is not infinite. As billions of years pass in silence, the very core of the Sun is slowly, irreversibly changing, choking on the dense, heavy ash of its own creation, inevitably setting the stage for a catastrophic, apocalyptic internal collapse. For roughly 10 billion years, the Sun remains locked in a majestic, terrifyingly violent state of perfect balance, functioning as a stable main sequence star. However, this magnificent era of golden light is completely finite, fundamentally limited by the inescapable reality that every single fusion reaction leaves behind a heavy, accumulating residue. Every single second, as hundreds of millions of tons of hydrogen are violently smashed together and converted into pure radiant energy, a dense, subatomic byproduct is abandoned in the absolute center of the 27 million degree Fahrenheit core. This byproduct is helium. In chemistry, helium is a colorless, odorless, and completely inert noble gas, the second lightest and second most abundant chemical element in the observable universe, characterized by an atomic nucleus containing 2 protons. The scientist who first mathematically mapped out the exact, horrifying consequences of this accumulating stellar ash was the brilliant German-American astrophysicist Martin Schwarzschild. Schwarzschild's supreme importance to the field of stellar astrophysics was his pioneering, revolutionary use of early electronic computers to calculate complex, multi-layered stellar models, allowing humanity to mathematically predict the precise evolutionary track a star takes when it finally exhausts its hydrogen fuel and begins to swell into a monstrous red giant. He conducted this paradigm-shifting theoretical modeling at Princeton University. Geographically situated in the Piedmont region of central New Jersey, Princeton sits on a strategically elevated ridge between the Millstone River and the immense Delaware River basin. Historically, this heavily forested, rolling terrain served as a vital, highly contested crossroads during the American Revolutionary War, culminating in the Battle of Princeton in 1777, where George Washington utilized the naturally defensible, elevated topography to outmaneuver British forces. This geographic positioning, safely insulated from the immediate naval bombardments of the vulnerable Atlantic coastline yet connected to the vital logistical corridors between New York and Philadelphia, allowed Princeton to evolve into an untouchable, secluded intellectual fortress, attracting the greatest mathematical minds on the planet to unravel the secrets of the cosmos in absolute isolation. Within the quiet academic halls of Princeton, Schwarzschild utilized a fundamental principle of physics known as the ideal gas law to explain the dying days of the solar core. The ideal gas law is a foundational scientific equation of state for a hypothetical ideal gas, establishing that the outward pressure of a gas is directly proportional to its temperature and the total number of particles it contains. In the core of the Sun, 4 individual hydrogen protons are continuously fused into a single helium nucleus. Because of this, the total number of individual particles in the core is steadily, relentlessly decreasing over billions of years. According to the strict, unbreakable mathematical rules of the ideal gas law, a drop in the number of particles inevitably causes a catastrophic drop in outward thermal pressure. As the outward pressure plummets, it can no longer support the unimaginable, crushing weight of the roughly 4.4 nonillion pounds of stellar plasma pressing down from above. The delicate balance is broken, and gravity begins to win. The core of the Sun violently begins to collapse inward upon itself. This terrifying, inward gravitational collapse generates immense friction, forcing the dead helium ash to compress incredibly tightly, which in turn causes the core's internal temperature to skyrocket from 27 million degrees Fahrenheit to a blistering, apocalyptic 50 million degrees Fahrenheit. This concept of utilizing heavily engineered mechanical compression and intense internal pressurization to survive against a hostile, crushing external environment was perfectly mirrored in the strategic bombing campaigns of the Pacific Theater during the Second World War by the Boeing B-29 Superfortress. Designed specifically to span the vast, unforgiving distances of the Pacific Ocean and deliver catastrophic payloads onto the Japanese home islands, the B-29 was a mechanical leviathan measuring 99 feet in length with a staggering wingspan of 141 feet and 3 inches, displacing a gross weight of 133,500 pounds when fully loaded for combat. To propel this massive aluminum fortress through the sky, it was equipped with 4 monstrous Wright R-3350 duplex Cyclone 18-cylinder, twin-row, air-cooled radial engines, each equipped with General Electric turbo superchargers and generating an earth-shaking 2,200 horsepower. These mechanical beasts drove massive four-bladed constant-speed propellers to push the heavy bomber to a maximum speed of 357 miles per hour at an operating altitude of 30,000 feet. Its primary offensive capability consisted of an internal bomb bay capable of carrying up to 20,000 pounds of high-explosive or incendiary ordnance, heavily defended by an intricate, remote-controlled analog computer fire direction system that directed 12 0.50 caliber Browning M2 and heavy machine guns housed in 4 remote-controlled twin turrets and a manned tail emplacement, alongside a single 20mm M2 cannon. Unlike any bomber before it, the B-29 completely abandoned the freezing, open-air fuselage design, relying instead on a revolutionary, highly complex pressurized cabin system that used engine-driven superchargers to forcibly pump compressed, heated air into the crew compartments, maintaining a survivable, high-pressure internal atmosphere against the freezing, oxygen-deprived, deadly vacuum of the stratosphere. Just as the B-29 Superfortress had to aggressively generate intense internal pressure to push back against the lethal, freezing emptiness of high altitudes, the collapsing core of the Sun uses its extreme, newly generated 50 million degree heat to aggressively push back against the crushing weight of gravity. However, this apocalyptic spike in temperature radiates violently outward from the dead helium core and slams directly into the thick layers of unfused hydrogen gas sitting immediately outside the core. This intense, radiating heat is more than enough to force the surrounding shell of hydrogen to overcome the Coulomb barrier, violently igniting a secondary thermonuclear reaction known as hydrogen shell burning. This newly ignited shell of fusing hydrogen burns much faster and significantly hotter than the core ever did, generating a monstrous, unprecedented wave of outward radiation pressure. This colossal outward force utterly overwhelms the inward pull of gravity in the Sun's outer layers. The previously stable hydrostatic equilibrium, which had held the star in perfect shape for 10 billion years, is violently shattered. The sheer force of the shell burning physically pushes the entire outer envelope of the Sun millions of miles out into space. As the outer layers are forced to expand, the gas rapidly loses pressure and cools, changing the blinding white-yellow light of the photosphere into a dull, menacing, and bloated orange. The Sun has officially left the main sequence. It is actively swelling into a subgiant star, initiating an unstoppable, catastrophic expansion that will mercilessly engulf the inner solar system in a terrifying wave of fire. With the delicate balance of hydrostatic equilibrium permanently shattered by the ignition of the hydrogen shell, the Sun officially leaves the main sequence and begins an apocalyptic transformation. The colossal wave of outward radiation pressure forces the star's outer layers to physically balloon outward into space. Over the course of millions of years, the Sun's diameter expands from roughly 864,000 miles to a monstrous, bloated diameter of over 150 million miles. This swelling transforms the Sun into a red giant. As this massive envelope of plasma expands, it naturally cools down, changing its color from a blinding yellow-white to a deep, menacing, and ominous red. In its relentless physical expansion, this fiery tidal wave easily crosses the 93 million-mile void of the inner solar system, completely incinerating and absorbing the rocky orbits of Mercury and Venus, and brutally boiling away the oceans and atmosphere of the Earth, leaving nothing but a scorched, dead cinder spinning inside a terrifyingly bloated stellar envelope. While the outer layers are physically swelling to gargantuan proportions, the dead, inert core of the star is experiencing the exact opposite fate. The core, entirely composed of accumulated helium, is relentlessly collapsing inward under the crushing, unfathomable weight of gravity. The chemical element involved here is helium, waiting to be fused into carbon. In chemistry, carbon is a nonmetallic, tetravalent element bearing the atomic number 6. It is the fundamental, absolutely critical building block of all known biological life in the universe, possessing an unparalleled, unique chemical ability to form highly stable, complex, and infinitely varied molecular chains and rings. However, before the helium can fuse into carbon, the collapsing core hits a bizarre, mathematically impenetrable wall defined by quantum mechanics, known as electron degeneracy pressure. This foundational physical concept is rooted directly in the Pauli exclusion principle, a quantum mechanical law stating that no two identical fermions, such as electrons, can occupy the exact same quantum state simultaneously. As the crushing weight of gravity violently squeezes the dead helium core, the electrons are violently stripped from their atomic nuclei and compressed into an unimaginably tight space. When the electrons are packed so densely that they literally cannot be squeezed any closer together without violating the laws of quantum physics, they generate a terrifying, outward mechanical force that halts the gravitational collapse. Crucially, unlike the thermal pressure of a normal gas, electron degeneracy pressure is completely independent of temperature. The astrophysicist whose vital importance to the field was mathematically defining the absolute limits of this quantum pressure was Subrahmanyan Chandrasekhar. Chandrasekhar's supreme importance to stellar astrophysics was his mathematical proof that electron degeneracy pressure could only support a dying star's core up to a highly specific unbreakable mass limit, roughly 1.4 times the mass of the Sun, which fundamentally dictates whether a collapsing star becomes a white dwarf, a superdense neutron star, or a black hole. Born in Lahore, British India, Chandrasekhar was an unparalleled child prodigy who formulated his groundbreaking, paradigm-shifting mathematical limit at the astonishing age of 19 while traveling alone by ship to England. A deeply disciplined, elegant, and uncompromisingly rigorous theoretician, he faced fierce, humiliating public opposition and academic ridicule from the established astronomical elite of the era, yet he remained steadfastly devoted to the absolute truth of his equations, eventually immigrating to the United States where his undeniable, world-altering brilliance ultimately earned him the Nobel Prize in Physics. Chandrasekhar conducted decades of his intensive theoretical research at the University of Chicago, specifically operating out of the Yerkes Observatory. Geographically located in Williams Bay, Wisconsin, the observatory sits on the elevated, heavily forested northern shores of Geneva Lake, a massive, incredibly deep freshwater basin violently carved out of the bedrock by the retreating Michigan lobe of the colossal Wisconsin glaciation millions of years ago. Historically, this specific remote topography provided a vital strategic advantage for delicate astronomical observation. Situated roughly 90 miles northwest of Chicago, the sprawling lake effect and the dense, surrounding woodland canopy acted as a natural atmospheric stabilizer, locking the air currents in place, while the extreme geographical distance completely insulated the observatory's delicate, massive refracting telescope from the crippling, blinding light pollution and the violent industrial vibrations of the booming Midwestern metropolis, allowing astronomers to peer into the dark, violent depths of the cosmos with unparalleled, uninterrupted optical clarity. Deep within the red giant, supported entirely by the quantum mechanics mathematically mapped by Chandrasekhar, the highly compressed helium core cannot expand. Because it cannot expand to cool itself, the intense friction of the surrounding hydrogen shell burning causes the core's internal temperature to skyrocket to an apocalyptic 180 million degrees Fahrenheit. At this precise thermal threshold, the helium nuclei are finally moving fast enough to violently overcome their own electromagnetic repulsion, as shown previously. They smash together in a thermonuclear reaction known as the triple alpha process, violently fusing 3 helium nuclei into a single nucleus of carbon, releasing a massive burst of gamma radiation. Because the core is locked in place by electron degeneracy pressure, it does not respond to this newly ignited nuclear fire by physically expanding and cooling down. Instead, the trapped heat exponentially increases the rate of fusion, which further spikes the temperature, creating a catastrophic, unstoppable runaway thermonuclear explosion. This terrifying event is known as the helium flash. In a matter of minutes, the degenerate core unleashes a flash of raw thermonuclear energy equivalent to the total light output of the entire Milky Way galaxy. However, this apocalyptic explosion is completely absorbed by the immense, heavy outer layers of the star, completely hiding the violent flash from the outside universe. The bloated, monstrous, and unstoppable physical expansion of the dying sun into a red giant, dominating the entire inner solar system by sheer, overwhelming mass, reach, and destructive capability, was perfectly mirrored in the strategic nuclear deterrence doctrines of the early Cold War by the deployment of the American Convair B-36 Peacemaker. Conceived in the darkest days of the Second World War as a transcontinental, intercontinental fail-safe weapon, the B-36 was an apocalyptic, heavy strategic bomber of unprecedented, staggering proportions, measuring 162 feet and 1 inch in length with a colossal wing-sweeping span of 230 feet, displacing a terrifying gross weight of 410,000 pounds when fully loaded for a global nuclear strike. To heave this mountainous aluminum fortress into the stratosphere, it was equipped with an incredibly complex, hybrid power plant consisting of 6 monstrous Pratt & Whitney R-4360-53 WASP major 28-cylinder, air-cooled radial piston engines, each generating 3,800 horsepower and turning massive 19-foot, 3-bladed pusher propellers mounted on the trailing edge of the wings, completely supplemented by 4 General Electric J47 GE-19 turbojet engines, housed in twin underwing pods. This deafening 10-engine mechanical beast pushed the bomber to a maximum speed of 435 miles per hour at an untouchable operating altitude of 43,600 feet, allowing it to comfortably cruise above the effective engagement envelope of early enemy interceptors and anti-aircraft artillery. Its primary, world-ending offensive capability consisted of 4 massive internal bomb bays capable of carrying an astonishing 86,000 pounds of conventional high-explosive ordnance, or the largest, most devastating thermonuclear gravity bombs ever constructed by the United States arsenal. Because of its massive, sluggish airframe, it was heavily defended by a highly advanced, remote-controlled analog fire direction system that coordinated 6 retractable, heavily armored cylindrical turrets, alongside radar-guided nose and tail emplacements, all armed with twin 20mm M24A1 automatic cannons, effectively creating an impenetrable, 360-degree hemisphere of defensive kinetic firepower. Just as the B-36 Peacemaker utilized its sheer, overwhelming geographical reach and massive, bloated airframe to completely dominate the global strategic airspace and project total annihilation from untouchable distances, the red giant sun uses its newly unleashed shell-burning energy to physically swell outward, creating a monstrous, bloated envelope that effortlessly reaches out to swallow the inner planets in a tidal wave of fire. Following the apocalyptic, completely contained detonation of the helium flash, the furious inner mechanics of the sun temporarily stabilize. The star settles into a phase of burning helium into carbon and, to a lesser extent, oxygen within its core. In the strict realm of chemistry, oxygen is a highly reactive, non-metallic element belonging to the chalcogen group on the periodic table, bearing the atomic number 8. While on Earth it exists primarily as a life-sustaining, colorless, and odorless diatomic gas absolutely critical for biological cellular respiration. In the deep, violent heart of a dying star, oxygen is forged under unimaginable pressures and temperatures, acting as a heavy, terminal ash that the Sun simply does not possess the gravitational mass to fuse any further. As the helium in the core is relentlessly consumed, creating an ever-growing accumulation of inert carbon and oxygen, the thermonuclear fires begin to stutter and fail. The Sun's core contracts and heats up once more, but it will never reach the staggering 1 billion degrees Fahrenheit required to fuse carbon. Instead, the heat radiates outward, igniting dormant shells of helium and hydrogen surrounding the dead core, pushing the star into the asymptotic giant branch phase.